I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism podcast, an exploration of the past, present, and future of material science. My name is Taylor Sparks. I'm a professor of material science right here at the University of Utah, and I'm here with my graduate student, Andrew Falkowski. How are you, man?
Doing pretty well. It's nice and crispy here. Fall is here. I'm not sure what it is. I don't know if I've been conditioned by school, but I always feel like the fall is the start of the year.
It does. It feels that way. And while it's cool here, in fact, that is up. We have these amazing yellow leaves right now, but there's a foot of snow in the mountains. It's this amazing contrast of bright yellow and white snow. But we are joined by somebody who has none of that, who has arguably the best weather in all of America down in Los Angeles. We are joined by Christopher Melnyk of CalNano. Chris, how are you, man?
Oh, very well. Thanks so much. Pleasure to be here.
Well, we're psyched to have you on the call today. CalNano has been a friend of the show for a long time. We've learned a ton from you guys. We're very interested in ceramic processing, among other techniques, right? And I had a chat with you guys recently about a new technique. And as you were describing it to me, I couldn't quite wrap my head around it because it sounded impossible to me. Today, we're going to talk about a blend of SPS sintering, which our listeners know and love. And if you don't, we'll put a link in the show notes to our previous episode. But that is now, you found a clever way to combine that with something that looks a bit like additive manufacturing. In other words,
Correct.
We don't have to settle for a single pressed disc that's all the same phase, all the same material. We can actually have different regions to make devices and things like that with this new technique. Am I getting that right?
Absolutely. Well, there's actually 2 or 3 different kind of approaches that we can discuss in more detail. But yeah, so one of them we can add different materials. One's a little more difficult to do so, and we can get more complex geometries. So it's a trade-off.
Okay, let's dive into it. Maybe from the get-go, help me understand why we need this. Why is it that multi-material manufacturing is important? What's wrong with just the old school approach of pressing a disc of one material, chopping it up, taking another material, pushing those together, bonding them, connecting them in some way? Why is that not ideal?
Well, I guess, right out of the gate, one of the main issues is just the economics of that. So if you can reduce secondary processing steps, then obviously that's a benefit. If you can reduce machining, that's a benefit. But as we get into the more difficult material systems that are driving most of the development these days, the materials can't, the applications stand to not allow them to be bonded or bolted or welded. If they're dissimilar materials, aircraft stuff, for instance, is, notoriously riveted together for, there's not a lot of welding going on for thermal expansion reasons, fatigue reasons. And so having choice materials and choice areas, joining things like ceramics to refractories, is a big advantage.
Yeah, I've seen a lot of commentary these days. A lot of people are still interested in finding new materials, but some people think that we've exhausted most of the really good materials that are out there and that a lot of the future is actually combining novel materials together into these more complicated structures where you can tailor properties depending on the location within the part. And this seems like a sort of technology that maybe is a step towards that, especially with the power of SPS too.
Absolutely. And also just maximizing the potentials, when you get into the microstructural manipulation potentials of getting to nanograde materials or nanocomposites, then we're taking certain materials that you may thought you knew, but can, push the boundaries of those a little bit further than historically possible.
So I'm kind of curious, when there's a new technology, I'm always looking for that killer app. Like, what is the application where this is going to change everyone's mind and be like, dang, this is the right new tool for this? What's the killer app that you see for this new approach of SPS, but with different regions?
Well, one that kind of jumps right out is in the world of tooling for things that require, like one example would be like die cast tooling or forging toolings and things like that, where you might have to have a high heat flux where you need high thermal conductivity, getting material heat in and out, so it needs to be hot for the initial consolidation of a part, but then it needs to cool down quickly. But then there's also a high wear or abrasion on the very surface where you might want to have like a copper core as an example with cooling passages through it. But then on the very surface of that part have tool steels that can take the wear of the application itself.
Okay. So we're going to get into how the tech works, but just one last thing setting this up is it sounds then if you can do something both in the core and at the surface, that means that you're able to spatially, both in the Z direction, say going up in the part, you're able to change the variation in the Z direction, but also in the XY, like we have full capability of putting materials in different places essentially.
100%. Well, with the selective powder deposition, you do the binder jetting kind of approach, which is the other version, a little less on the different materials. It might be possible. I'm not an expert on the binder jetting side of it, but with the selective powder deposition, absolutely, because you're basically just printing 2 or 3 different materials, like a dot matrix printer, as you're going over top of a mold that's dropping down layer by layer. So if you think your conventional powder bed printing, but the difference is you can drop very precise locations of different materials if you want.
Way cool.
And what sort of resolution do you get with that?
On that one, we have about a 200 by 200 micron on the XY and then 80 micron on the Z, or Z, as my Canadian friends like to call it.
That's pretty precise. And what sort of cross-sectional area can you do? I know SPS usually, in the past, a big limiter was the size of the part you could do. I know that there have been some newer machines that can go bigger, but
I think CalNano has one, right? Don't you guys have a pretty big component you can make?
Absolutely, yeah. So we have there is a model that's a little larger than ours, but we have the largest commercially available SPS in North America now, and so we can do 16, 17-inch cross-section diameter parts. So we're making 67, 70 kilogram billets out of some high temperature chrome alloys and stuff like that. But to answer your question, sorry, on the printing side, the 2 different the 2 different processes have their own limitations and their own. On the binder jetting side, it's as big as you can binder jet and then fit into a mold or the cavity that would be, in our case, 16, 17 inches in diameter. On the selective powder deposition side, it's more in the 5 or 6 inches across kind of range, and that's based on the print head size limitation, which could be augmented. It's just the current hardware limitation.
Right.
So let's get into these different approaches for laying down different materials. To do so, I think we have to provide like a quick 1-minute primer on SPS for those that aren't familiar with it. So essentially the idea behind SPS, you've heard it before probably, but you're taking powders, you're putting them into a die and you're heating them until they sinter. That sounds like regular old hot pressing. The catch is that instead of heating up the entire die in some large cavity of a furnace where the whole thing is heating up, which tends to be slow, right, which leads to large grain size and things like that. The catch here is that you are locally heating the die itself or the die in the powder by passing an electrical current either through just the die, or if the powder is conductive, some of that current is going to go through the powder. And so you can get much faster heating rates. Okay, so people, just if you're not familiar with the technique, you're able to squeeze on it while you're heating it, and the heating is coming from an electrical current. Now, with that sort of in mind, let's think about how we're going to place the powders in here. If you're doing, say, a deep part, right, something like an inch deep, I don't know how deep you can do these things, right? 16-inch cross-section, I don't know if you're going to do even a half-inch deep. Do you run into the challenge of having to move the die down as you're depositing the powders, or can you have it placed all the way down and will the print head reach into the corners? You see what I'm saying? Like, I'm not quite sure on the print head if it's going to be bumping into the wall or if you have to be bringing the die down as you place the powders.
You do. You bring the punch down and the die stays fixed. So the die isn't moving and then the punch goes down. So initially the bottom punch would be flush with the die. So it's raised all the way up. So it just makes like a flat surface. And this is in the selective powder deposition version. And then you print your first layer and then the punch lowers by that thickness. And then you print another layer and then the punch lowers by that thickness. So at this point, you just have loose powders that have just been placed very precisely as it goes down further and further and further. And in that case, you can get quite high. I don't know the exact Z height displacement potential on that, but we're not limited to just a half inch or anything. Like it's several inches on that machine. Of course, that's loose powder. So of course, at that point, it's only a relatively low tap density. And so then once it's sintered, it's going to be compressed substantially down, like 3-to-1 or 4-to-1, depending on the material system. So you're going to lose a lot of that height from the print state to the densified state.
I'm curious, since this is a new technology, maybe you haven't investigated this, but I'm curious how much settling and reorganization of the particles there are as the punch is moving down. Have you seen any of this? For example, if you knew what the resolution was when you put down the particles, at least you think you know what it was, does that sort of match roughly 1-to-1 to the final part? Because you've also got sintering and shrinkage happening. I'm just a little bit curious.
Yeah, definitely. I don't have a quantifiable number that says, you lose this much resolution over this many layers or anything like that. But for sure, there's those things to contend with, and just naturally with the powders that are closer to the die walls, there's going to be more things happening and interacting with that powder load as it drops down layer to layer when it's near a powder, when it's near the wall, versus if it's just freestanding in the middle, surrounded by other powder, if that makes sense as well. So, and then when it does compress, the flow of the material inside is not super obvious. It's, we're applying uniaxial force directly down in the z-axis, but the flow of the material internally isn't exactly perfectly, north south. There is some hourglass shaping going on in there, so predicting that is important as well.
And do you get settling as well? Do you have to be really careful handling it, moving it from the device to the SPS, or is this all one unified device such that as soon as you lay that down, the rollers can move out and you can press, or is handling even a factor? Or is it?
No, it is. But the technique there is you put the top punch on and you put it under some compression first, so you're holding it all tight. Yeah. So we've actually shipped parts that have been printed, in large distances, so we can actually like apply a pressure and then it can be transported.
Okay, very cool.
You just maintain a low pressure, low relatively to comparatively to sintering pressures, but you just put a load on it under spring tension and then you can ship it.
So that's selective powder deposition. And
Yes.
binder jetting is not so different, right? You're also putting down particles, but I don't know if it's happening. I don't know how you guys do it. I think I've seen it done different ways. You can either have the powder pre-mixed with a binder, or you can put the powders down and sort of spray a binder on top of it. But it's essentially the same approach, but you're adding a glue, right? Some sort of binder that's going to hold it together. What are the pros and cons? Like con to me, obviously, is when you add binder with ceramics, at least you very often want it fully dense, and now you've got one more thing to get rid of in the densification process. But I guess the benefit might be better holding that resolution of whatever the part is that you were trying to achieve.
Indeed, and again on the binder jetting side and that hybrid approach, our collaborating friends at Normat out of France are really the experts on this, and they have essentially two versions of how they can do this. One is where you're printing the reverse mold, and so you're actually using the binder jet to produce essentially like a casting mold, and so then that your material and your part is the cavity inside of it, and then so you're actually just printing very precise molds. And then the other one's more conventional, as you described, where you're actually printing the material with a binder that's going to be your final part. In which case then the material is removed, debinded, and sintered together in one process, in one step inside of the SPS. And then you're getting the densification that's like quasi-isostatic, because you still have material around it that's a support material that can then be sacrificed.
Gotcha. So thinking about this, something that immediately would stand out to me as a challenge would be, how do you sinter two materials that might have different melting points, or might have different sintering behavior? I'm familiar with sintering curves, but now you have your co-sintering, or maybe, and this could extend between 2, 3, 4. How is CalNano approaching that, and what are some of the challenges specific to this particular technology in that regard?
100%. And again, it's, it starts getting complicated because we're talking about 2 or 3 different process paths, and I'm going to add two more. So in one case, sometimes what you do is you can't do everything all the time, and so sometimes you have to do things twice. And so sometimes if there are significant differences in temperature, you might have to just densify the part that's at the highest temperature first, and then bond to it, in a secondary step. And so before we get into even the 3D side of things and the additive, sometimes we're just molding materials around preformed components. And so if you want to add 2 different parts together, sometimes we just start off. One example we did recently is we have a ceramic tube. I have to be careful what I share. Obviously, we do mostly contract work for people, so I have to be careful what they want to. The application is a heat sink of sorts, and they want there's a ceramic tube preform, multiple ceramic tubes, and then they want copper, a copper block, basically SPS'd around those ceramic tubes. So in that case, we're not sintering the ceramic tubes. In this case, we start with those as already existing solid forms, and then we sinter the copper around it. So that's how you end up with multi-materials in one part. That's the most simple way. The other side is when you get into asymmetrical tooling designs where you can actually create hot spots and cold spots. So normally you want to prevent thermal, gradients from forming from asymmetrical tooling or just odd sizes, but you can create it on purpose. And so if you need to, you can actually do some tricks because it's current density based. We're applying current, which is what's driving the heat. So the more surface area that you have, the less concentrated that energy is, and the less heat it's going to produce. And so if you have a reduction in cross-sectional area in your tooling, it's actually going to get hotter. And so you can actually produce purposeful hot spots to help sinter the hot thing, and keep cold spots to help not melt the cold
this
thing.
gets really hard. And then you have the additional complexity that because this is SPS, the current, right, is going to take the path of least resistance. So you have materials that are more like, if they don't have the same conductivity, they're going to have different Joule heating in and of themselves, right?
What role does modeling play?
Well, obviously, as you get into this, a lot of the stuff is more on the experimental side, and so the modeling does help, but a lot of times, in our experience, the modeling isn't quite there. Well, I'm sure people have the capability, but the modeling that we've had in house has been a little on the short end of being able to model a lot of these things because it's just a little too complex for the inputs. So a lot of it's just trial and error.
That's a hard problem.
Yeah.
I wonder, have you guys ever inserted insulating barriers between the punch and the powder? I've seen that done in other places sometimes. And normally you'd be like, well, why bother? Because you want the heating to be as uniform as possible. And heating from the die itself only means that you have a gradient going inward. But here, where you've got multiple phases that you're trying to control the shrinkage independently of, I wonder if it would be worth it to put an alumina sleeve around it or something. There's different materials out there you could put.
In short, absolutely. And so, you mentioned in the onset of the brief description on SPS, the heating mechanism, the benefit over conventional sintering where you have heat coming in. How much of a benefit is the benefit before you can call it no longer a benefit?
Yeah, it might start to hurt you here.
Yeah, no, it's fine. And it's because, when you in the conventional sense, you mentioned like if it's in a vacuum furnace, for instance, you're waiting on infrared heat to go through the vacuum to hit the outside of a die wall to then soak into that die to then eventually get to the part. And so it's a long process. If we look at the worst case scenario in SPS where the current is going through the die alone and not the material, well, it's still an intimate contact and generated very quickly. So the ramp rates and the time at temperature are still significantly better than a conventional sintering where you have to wait for all that heat to come in from the outside. So even if you limit yourself with current blockers, as you described, to the material only going through the tooling, you're still way ahead of the other competitive ways of doing these things.
I would think another big advantage is usually a big potential problem is if you're waiting so long, right, like at your interfaces, you're going to get a diffusion bond. But if you have so much residual heat in a normal furnace approach, you're likely to get a pretty big interface and probably some deleterious phase in between those. But do you find that you get pretty clean separation between the materials with SPS? I guess that's a tunable parameter, but...
Yeah, and that really depends on the two material systems. And so, sometimes some of our customers will dig deep into that and look at the interfaces and figuring that out and what kind of secondary phases are being produced in between those materials. Some of that gets above my pay grade on the science level, but sometimes you can imagine just from powders being laid out, there's a mechanical kind of effect going on as well. It's almost like Velcro. You have your hooks and loops happening where you have fingers reaching up and down that are holding each other, but there's definitely diffusion bonding happening as well and some mass transfer, and then that gets into the pulsing versus non-pulsing and the different power deliveries and then the different material systems, which ones like to play together, which ones don't. I mean, carbon diffusion is always a topic. If you're using graphite, isn't it? It's not between the powders, but it's always a topic as well.
So looking through some of the materials you sent us to read on this, one of the brochures talks about that you can do 3 different powders up to 100 millimeter diameter. So I'm curious, have you guys explored printing, let's say, a ceramic powder, which is going to have a pretty good corrosion resistance, with something like a metal, which might have a lower corrosion resistance, such that you could take the final part and instead of just having, say, copper channels running through it, you could have actually dissolution of that metal phase, and now you've got cavities running through it as a way of making even more complex parts with internal shapes?
Yeah, absolutely. Now, how much of that we've done ourselves in house, I don't know. I haven't done it myself personally, but absolutely, that is how that can be done. So there's two ways. One is the internal cavities can be a ceramic material that's just a significantly higher temperature material that's not going to sinter or fuse compared to the materials
And then you
around
just
it,
knock the
and then
powder
it's
out, you
just
mean?
cleaned out. And
Yeah.
you just and that's just one way. And then the other way could be that you use things like salts,
Yeah.
and things like that, where they will densify and then they can be dissolved out after. There's a few different ways you can do that.
About is CalNano the first to be combining these two techniques? And about when did that happen?
Well, I don't know. I don't think so, because I mean, in the sense that the Aerosint, they by the time we discovered them and their printing, they had already, in some small scale way, had already taken their selective powder deposition, which was used for just conventional sintering as well, and already done some of the SPSing side of it. And the same with Normat. I think with their approach using the binder jetting, they've done that, and they have their own SPS as well. So I don't think we're the first ones to do it. Of course, that's international players. We might be the first ones doing anything like this in North America.
Yeah. Yeah, I just kind of asked because I was at a nuclear startup a few years ago, and we were trying to create a complicated ceramic part. It was zirconium carbide, and we were trying to have internal channels. And so to get to the melting temperature of zirconium carbide, or even close to the sintering temperature, right? That's like
Hot.
very hot. So to get it up to 2700 C, we needed to go through an SPS route. But getting the individual channels, because we were trying to have basically gas flow through this, was really a challenge. It was hard to get them to be uniform or have anything. I think we were using like pins or something in there, and there was all sorts of deformation happening. Seems like it would have been a great technology to have access to.
Yeah, and we hear that story a lot. I do the presentation on this. I got guys who had all these technical challenges of brazing and joining dissimilar materials or producing things back in the 80s, 90s, 2000s, and like, oh man, if we only had this tool then.
So I've got a question for you, Chris. With this technology, which is really a new manufacturing route, are you familiar with the manufacturing readiness levels? Right. So there's TRLs, which is technology readiness, but then there's one specifically for manufacturing. For our listeners, I'll just read the first couple of these. Like MRL1 would be like, okay, the basic manufacturing implications are identified. 2 would be that the concepts are identified. 3 would be your first proof of concept. 4 is taking that and now producing the technology, but in a laboratory environment. 5 is then moving that to a production relevant environment, and then having a production system or a subsystem would be TRL or MRL6. By the time you're at MRL7, now you're doing it in a representative environment where you're considering things like cost and supply chain, like getting way down the line. Where is this? And we could keep on going. Like there's 8, 9, 10, right? Where is this approach? Because you're the leader of business development over at CalNano, which I'm thinking is new technologies. How mature is this? If I'm a company, if I'm a General Electric or somebody out there wanting to use this, where is this technology at?
Well, I guess, how I answer that and how our friends at, say, Normat or Aerosint might answer that might all be a little different depending, because, again, we're talking about 2 or 3 different technologies, and how much we've dipped our toes into each one of those buckets is a little different as well. So, for instance, I know at our Normat, they have parts that are currently in qualification stages for aerospace and energy and defense sectors. So they have parts that are actually currently being qualified right now that are produced this way. That's what the binder jet version. On the Aerosint side, we've done mostly preliminary evaluation stuff with the thing, but I'm not sure how far they've gotten with it. So I'd say pretty early in the stages still, but I might be sandbagging the answer compared to where they are on some of these things.
Okay. So if I'm a big company and I'm hearing this episode, I'm like, boy, we have an application that would benefit from this. What does the timeline typically look like? Do you start out by sending the powders and then saying, let's figure out how they sinter, let's establish sintering profiles for these powders of interest, and then you look at diffusion, and you look at resolution? Like, I don't know, I'm just putting words in your mouth. Like, what would the process look like before they could actually get a part manufactured?
Again, it really depends on what the novel part of this is. If it's an established material system that we have lots of experience just doing the sintering of, then we might be starting off further ahead, because we've done thousands and thousands and thousands of SPS runs in different materials. So if it's something that's pretty common and the challenge is just the shape, then the focus might be very different than if it's a novel material system combining two different novel material systems. Then more of the energy might go on the front end, figuring out the proper sintering balances and mechanisms involved there. So again, it's case by case, but typically you would start off by just contacting us, sharing what your project is, and but you basically hit it. We're going to start off all the time with optimization runs, figuring out what cause and effects are going to get us the whatever the design criteria is. I want to say full density, but often we're getting requests for partially dense parts, 70%, whatever. So whatever the goal is, figure that out, and then start adding the complexities one step at a time, whatever they may be.
I've got another question. So far, we've talked about competing different objectives of having different phases. Like one you've alluded to is that you have to have a structural component, has to stay together, but you also care about thermal transport. You mentioned that. Have you considered other properties like functional materials? The ones that come to mind are things like structural batteries, right? This is a pretty interesting area right now in material science where you're going to print the airplane wing, right? But the wing itself, while it's structural, it's also made up of a bunch of, say, electrochemical cells or something. Have you looked at other of these sort of functional applications where it's structure plus function?
It's a great idea. I've heard about it, thought about it, have done it. No, I think, these technologies are kind of a paradigm shift, and they just open up a, endless, infinite amount of new potentials. And so there's so many things that could be done that probably are all valid and great ideas. It's just a matter of picking and choosing some and putting the time and effort into them. And so since we're a service-based company, we don't do a lot of in-house development to make products ourselves and go to market with them. So we don't really run that. We kind of just do whatever people want us to do. So
in other words, if you're a company out there and you've got these ideas and you didn't know how to make those parts, now you've got a partner, right? Somebody could actually try it out for you.
Exactly.
Cool.
Yeah, and we love getting challenged. I mean, that's, the funnest one. So, I mean, hey, it's a business, so we'll take whatever business, people want to give us. If it's something that's simple, we'll do it. But it's fun getting the more challenging ones that are a little off the wall, because it really gets the creative juices flowing.
Okay. Maybe just to kind of wrap up, can you tell us a little bit about some of the intended applications and what people are using this technology for right now?
I mean, one that, is growing a lot, obviously, is in the defense space. And so that could be everything from the areas where we need to make lots of things that are very choice, high temperature materials, things like hypersonics, one-way payload delivery systems, rocket motor components, jet engine components, hypersonic applications all around have a lot of temperature and exotic material challenges, joining dissimilar materials, forming complex shapes out of materials that don't like to be machined. So their sweet spot for these technologies is really in the novel material systems, the HEAs, the refractory HEAs, combining with carbons, these materials that are really pushing the limits of how do you even make this stuff? How do you machine it? It doesn't like to do any of these things. So being able to produce them into net shapes is a huge leg up. Being able to produce multiple materials and then make them joinable, it's a huge leg up. So we're pursuing some larger efforts internally and congressionally for working on some hypersonic applications, as well as nuclear applications. The micro reactors you mentioned, those are gaining a lot as well for some of these things. Yeah, lots of applications on the forefront.
This episode is sponsored by California Nanotechnologies, or CalNano. I just want to point out that there's a really cool opportunity coming up. In today's episode, it was awesome because I've got one of the world experts in SPS, and I can just pepper him with questions, and it's so fun to sort of have that immediate feedback. And I think a lot of our listeners would like something like that. You'd like to actually talk to the expert, and obviously this is why conferences and trade shows exist. One of those that's coming up is the TMS 2026 spring meeting. We never miss it. It's going to be great. It's in San Diego this year, which is close to your headquarters. And CalNano's taking advantage of that. And you're actually holding an SPS sort of user meeting or workshop. It's going to take place directly after the TMS, so you can just book one travel, right? And it's apparently going to be the workshop one day where you're going to have the chance to learn about it, talk about it. That's going to be held in San Diego, near where the conference is at. And then that'll be on February 19th. But the next day, February 20th, there's actually going to be a tour of the CalNano facility where they talked about having sort of the world's or North America's largest SPS. You can actually go see it, right? They're going to have the opportunity for you to see these things, talk to the engineers, probably run ideas past them about potential projects where you could do together. So we are happy to point that out to our listeners, and we're going to be reminding you in the weeks to come. But for now, we recommend checking out calnanocorp.com, and you can find on their landing page somewhere more information about this workshop in the months to come.
And and one other thing to add to that would be that, we're going to have a bunch of world experts coming from all over the place, including Europe. We'll have visitors from one of our collaborating partners, Dr. Fritsch SPS out of Germany, who makes the most SPS units in the world by far. They're the manufacturer of our large MSP5 unit, as well as some others from our European partners. So if you're of interest, it won't just be about all the CalNano stuff that's happening, but we'll be including some of the great minds in SPS globally.
Awesome. That sounds great. Chris, it was awesome to have you here today. Look forward to the workshop. I'll be there, and look forward to seeing you at TMS, and we'll talk later.
Absolutely. Pleasure. Thank you, guys.
Yep. So today's episode, in addition to being sponsored by CalNano, is brought to you by the American Ceramic Society. We've been promoting them for a while. We want to remind you today that the Bulletin is American Ceramic Society's magazine, and we think it's a cool way to connect with not just scientists who are interested in ceramics here in the United States, even though the name sort of suggests American. This is much more than America, right? Actually, nearly 40% of the American Ceramic Society members come from outside of the United States. And the Bulletin is a way where you can actually bridge geography and material science, highlighting these international perspectives, trends, but not just from America, from abroad.
Yeah, and the October-November issue for this year on international markets is spotlighting Korea, and that is out this month. So don't miss out on the materials innovations and updates from around the world. You can do that, and you can find out by visiting ceramics.org/materialism to unlock full access to the Bulletin with a free ACERS membership. The Materialism podcast is also sponsored by Materials Today. You can visit materialstoday.com to stay up to date on the latest happenings in the material science field and read some of the fantastic articles that they've published. You can also head over to elsevier.com to find out more about their journals, books, conferences, and related programs.
And as always, we are so excited to have you guys a part of the show. I just got back from a conference where I met with so many listeners. It is absolutely unreal to be connecting with audience members from around the world. We would love to hear more feedback on what stuff you guys want to hear. You can find us at materialism.podcast@gmail.com or the @materialismpodcast on Instagram, or pretty much everywhere you want to find us. We are out there, and we love hearing feedback on the show. Special thanks to the people who make the music possible for this show, Alphabot and Kolobyte. We appreciate you. And that's it. We will see you guys next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world, and are bound only by their imaginations in manipulating those materials.